So good morning, everyone, and welcome to today's live lecture. I will immediately dive into some of the questions that people have asked in Piazza and then move on with going to the quizzes that we posted for this week's lecture. Okay. So for Piazza, there was relatively few questions, probably due to the midterm exam that happened last week. Nonetheless, like the three most important elements I want to quickly go through. The first one was a question why we can calculate the energy in different reference frames. So whether or not we can take velocities in body fixed frame or inertial frames. And there is an explanation in Piazza, but I put here also the mathematical explanation to this. The energy itself is completely independent of the choice of reference frame. So what I put here first is like, this is the energy if I calculate the velocity in I frame. Now I can also take the velocity in B frame and then transform it through the rotation matrix to the I frame. So this is equivalent to the velocity expressed in I frame. And if I do the multiplication of that, I get an inner product term of C transpose times C. So I rotate once from I to B and once from B to I. So actually it doesn't really matter. So these two things are just identical. That means it's independent of the reference frame of where I'm expressing the individual contacts. What is important, however, is that we have an I here. So it's always R dot between a non-moving point and the center of gravity. But that has nothing to do with the reference of where we are expressing this vector. The second question I want to quickly address was related to what is the meaning of a stacked torque vector. That's something that we're using in the script, but also during the lecture series here. We are using this very frequently. And what that means is, in essence, if I have a robot arm, so series of links, what I typically have is a actuator which is mounted here in the joint, and that actuator produces a torque on the following link and the counter torque on the previous link. Now, if we choose the generalized coordinate, so to describe the kinematics of the robot, if we choose that generalized coordinate, this QI, as the relative angle in exactly the direction where this actuator works. If I do this, then the torques that are produced by this motor pre-multiply the Jacobi transpose of where they are attaching. What results this in is into a torque vector which has on this I entry this tau I. So I just stack the torques 1 to the torques n for every single actuator, as long as I'm choosing the generalized coordinates exactly the way how the actuator works. As we learned, we can also have different descriptions of different selections of these Qs. So for example, I can also have a Q which is from the vertical. So let's call this phi, a different set of generalized coordinates. If I have a different set of generalized coordinates, there is a different linear combination of these tau i's that I see in my torque vector. So it's not just stacking the individual torques, but it's a linear mapping of the individual torques because the Jacobians are changing, obviously. This is related to the second question. And then the third question, that was actually a typo that we have in the slides. So whenever I was talking about the Lagrangian, what I did miss was the transpose up here. So you can also, as long as you have 0 on the other hand on the right-hand side of the equation, it doesn't matter because it's still 0. It's just like either you have a row or a column vector, but in the case where we have the tau vector on the right-hand side, which is a n by 1 vector, we have to have it transposed here. So I corrected this in the slides and uploaded them again. So this is for the stuff on Piazza, and we are now moving on with quick highlight on what, in my eyes, were the most important elements that we have been discussing last time. So this was from the week before. We derived equations of motion. So importantly was we ended up in different methods that produce this formula. Now, last week, what we did were two things. We, on one side, we looked at how can we express these dynamics equations of motion differently. So instead of looking at the joint space dynamics, can we also just look at the task space dynamics? The task space, very often, if you're talking about a manipulator, which is bolted to the ground, and what you're interested in is the end effector and how the end effector is moving, how the end effector is interacting. So it seems there was a glitch in Zoom. I hope everybody's back. Let me continue here. So what we did there was, in essence, moving from the joint space to this task space. And as I said, task space very often, particularly when you're talking about manipulators, is the end effector space, so end effector position orientation. And we formulated this equation here, where we have a lambda, which is the inertia tensor in task space. So if you're looking at the end effector, it's like if you had there an ellipsoid, an inertial ellipsoid at the end effector, which indicates the mass in linear directions and the inertia in rotation directions. And then we had also mapped Coriolis centrifugal and mapped gravitational parts from joint to task space equal to these task space forces. And then we looked at the control methods, which allow us now to leverage this description that we have, so this model knowledge, and build a controller that uses that in order to identify what kind of torque do I have to generate in order to move my system in a certain way while compensating for the dynamics of the robot. So in big contrast to a position control system, where essentially the feedback controller of the local position loops cancels out or tries to cancel out all the dynamics, in inverse dynamics control, they're trying to compensate for that by this model knowledge. So ideally, if you have a perfect knowledge of the model, you don't need any integrator gain. You can just like feed forward, define how the system should move, and then produce the torque that makes it move in that way. And if you go to literature, you'll find different ways of doing this inverse dynamics style of control. So the classical joint space inverse dynamics. Then when we do inverse dynamics in task space, people often talk about operational space, where you can also directly control this end effector motion and end effector interaction forces. And I showed you at the very end how all of that essentially can be summarized by a couple of quadratic optimization problems. And I think this is, in my eyes, this is a very important element here for you to understand that what we're doing in this joint space or task space inverse dynamics problems are nothing else than optimizing the torques, optimizing the motion such that a number of linear equalities hold. And what you see here, this joint or task space dynamics, this is nothing else than linear constraints on motion and on torques. So I brought up one slide at the very end of a video segment which summarizes this at once. So what you see here is for 3 methods, which are, like, in the end, they're all more or less the same, right? You have classical inverse dynamics, you have operational space control, and you have this quadratic optimization. And what we showed you here is that if you do classic inverse dynamics control, what happens is that you are taking this formula. So what you need to have is a desired acceleration in joint space. And this desired acceleration in joint space, that is typically evolving from a number of tasks that you want to fulfill. So you can already define the motion in joint space, but very often this is very hard to do. You can much better describe the motion in task space and end effector space. For example, you have a robot arm. I can tell you what the end effector of this robot arm should do. And then what I have to do is I have to identify what the joints have to do in order to make the end effector doing this. And then I do inverse dynamics. That's the approach here. So we are setting up A or the N tasks for describing this end effector motion. We're converting this into the joint space acceleration, and then we're doing inverse joint space dynamics. Now, depending on the dimensionalities of the task description, of the numbers of degrees of freedom that we have, so how many Qs exist, what this is doing is, in essence, solving a minimization problem, saying that what torque do I need to apply to my robot in order to make it move such that my end effector follows a predefined end effector acceleration, which comes in here, so through an omega, a W dot desired, and which solution minimizes the total acceleration, or the least square solution in the acceleration. We are separating the motion optimization and introducing this then into the inverse dynamics. Now, if you analyze the task space inverse dynamics or the operational space control, it's slightly different. And the difference is that the solution that we're getting there is not the exact same solution. It will do the same in task space. And if the system is non-redundant, so if I have a 6 degree of freedom robot arm and I define 3 linear motion directions and 3 rotational directions, the acceleration in these 6 directions, then I will get exactly the same solution, because there's no way of optimizing except for following that task as well as possible. But as soon as you have redundancy, or as soon as you can't follow it exactly, what happens is that the optimization that happens in the second or in the first solution is different. And we analyzed this, so we went through looking at what kind of null space projection matrices do we have here. This will also be seen in the next video segment, so it's going to be the exact same null space projection matrix that we will revisit in the floating base systems, and that we will revisit in collisions of robotic systems. And what this does is, if you look at what the Q double dot solution is, it is a weighted pseudo inversion in here. So instead of taking the Jacobi transpose at the pseudo inversion of the Jacobi, which is a least square minimization of Q, I have now a different weighted minimization here, which is producing a slightly different solution. there is one question here which says that a dot is missing in the classical inverse dynamics at W dot equals to J dot dot plus J dot Q dot here. Yes, it's correct. Thanks for pointing this out. Here, of course, we should have a dot. It is here. Yes. And then at the very end, what I introduced is the quadratic optimization. So we have seen now whatever we do, whether we do joint space or operation space dynamics, it is fulfilling the constraint that this equation of motion holds, or this equation of motion holds, while we want to optimize a certain objective and have certain constraints that are valid. And this is what we formulated here. So we said, okay, one linear constraint is that the torque must be equal to a linear function of Q double dot. One constraint is that I have a linear relationship with Q double dot that must be equal to a desired W dot. And then I have objectives, for example, the first one, minimize acceleration, but I can also just minimize my torque or any other objective I have. And if I look at this, I can then apply what we have seen in the inverse kinematic or inverse differential kinematics methods. I have a optimization, which is nothing else than A1 times X plus B equals to 0, and then A2 times X plus B2 equal to 0. So we have a number of linear objectives that we can now optimize, either using single task optimization, prioritized optimization, and so on and so forth. Now in here we have only 2 tasks, but believe me, if we are looking at way more complex systems, like a humanoid robot that has 80 degrees of freedom or something like this, you're going to have here a whole number of different tasks. So for example, you want to stand stable, you want to grasp something, you want to look at something at the same time, you want to keep a certain posture, you want to minimize your actuation torques, and so on and so forth. And this is now a framework which really allows us to properly integrate this into a holistic formulation that in the end is a generalization of what we've seen in inverse dynamics. And we're applying this today to rather simple setups, and then move on with floating-based systems and legged robots, where we see this in use more appropriately. So this is a quick wrap-up. We're going to go now into the individual quizzes that we had, which was done with one excavator that we have with us at the lab, and it was also, like some years ago, this was part of an exam question, so you can expect something similar to come. Typically, we will provide you also in exam. We say, okay, we have expressions for the equations of motion. We also derived position rotation Jacobians, so you don't have to do this. For recap here, if you look at the dimensionalities, so we have Q is R4 times 1. So we have the mass matrix. This is a 4 times 4 mass matrix. The position Jacobian is a 2 times 4 position Jacobian. So we are controlling X and Y. And we have the rotation Jacobian, which is a 1 times 4 Jacobian. Then the questions were, what joint torque is required for static gravity compensation, lifting 100 kilo, and what torque is required to accelerate upwards, and then some questions about uniqueness. So let's dive into this in more detail. So first, static gravity compensation. Static means your system is not moving. And that means we have no acceleration. We have also no Coriolis centrifugal part, so both of that is 0. So what I have is, in essence, my gravity part here that I derive in my equations of motion, this is directly the joint torques that I need to apply in order to just keep this arm somehow in the air. Second thing is I want to lift 100 kilograms. So that means I have to compensate for gravity, and I have to additionally produce an end effector force which corresponds to 100 kilograms. So I compensate for gravity, and I need to have my position Jacobian at this point P, the transpose of that, and multiply it with the force that we want to produce at that point. And this force is acting in vertical direction, so in y direction, with 100 times g, so times 9.81. One of the biggest mistakes that people are doing, or that I see very often, is that you don't know, is this now a plus here or is this a minus? In general, like having the right signs for external forces seems to be pretty tricky. What I typically recommend is if you look at the equations of motion. So we have mq double dot plus b plus g. This tau here on the left-hand side, this is what I give as an actuation to my system, right? So if I have a force that my robot has to exert on my environment, I have to increase my torque. So if I put my force here on the right-hand side, then this force must be the force exerted by the robot on its environment. So in other words, if I have to lift something, I have to produce a force which points upwards. I have to compensate for the additional mass that produces a force that goes downwards by producing a force that goes upwards. And this is why I have here a plus sign. And that's also to be seen in some of the next examples. Then C was moving it with one, or like accelerating it with 1 meter per second square upwards, and then while keeping x position and orientation constant. So what does that mean? We want to accelerate, so we have a desired w dot which points upwards, so we get now a motion. So we have 1 meter per second square that we want to accelerate upwards. We have a 0 rotation acceleration, and we have a 0 acceleration in x direction. This is my desired acceleration. If I want to define my desired joint space acceleration, all I need to do is I have to map now from task space to joint space. And this is done through the pseudo inversion of my Jacobian, where I have the desired acceleration minus coupling term, which is coming from the current state. And then once I have calculated my desired acceleration, I can simply insert this in my inverse dynamics, joint space inverse dynamics equation. Now the question is here, is this unique or not? And as we know, we have this JP, this is a 2 times 4 matrix. The JR is a 1 times 4 matrix. So in other words, we have here 3 times 4. So this can have maximally rank 3. So for sure, we have 1 degree of freedom, which makes the system redundant. In other words, I can change the way I'm moving my joints without changing the way I'm moving my end effector. So I have to take here, because of this 3×4, I have to take here a pseudo inversion, and I have a null space projection matrix and a Q double dot 0 that allows me to change the solution in Q double dot. However, I can change Q double dot without changing my W dot, but I cannot, the second inversion here, I mean, this is the second formula here. When we go to tau, once we fix Q double dot, we have only one unique solution. So there exists multiple solutions for Q double dot, but given a certain Q double dot, the torque is unique. There's a question in how can we make sure that the position in X and the rotation are constant? And wouldn't that mean that the velocity in X and rotation velocity have to be 0? This is absolutely correct. So if the velocity is 0, so let's go for the X. So X constant means that X dot equal to 0 and X double dot equal to 0. If you have, if you're defining here only something on acceleration without having a feedback on the velocity and a feedback on the position, all you can do is you can set this to 0 and you can start at the state where X dot is equal to 0. If X dot is not equal to 0, that means you are diverging from X. What you would have to do is you would have to define a feedback law here, which says my X double dot must be equal to my certain Kp times my X desired minus my current X at time t plus a Kd term times my X dot desired, which is equal to 0 minus my X dot at time t. So I would have to define a feedback law on X and X dot to determine the X double dot and then insert this feedback law in here. And by this, we could keep it constant. The same if you say we have joint limits or something, also then we have to define the limits that are on position or on velocity level. We have to move that through a feedback law, potential fields or something, up to the acceleration level in order to integrate this the way we have it here. Then we moved on with task space dynamics control. So exactly the same problem here. The question was what torque is required to accelerate with 1 meter per second upwards. And again, like orientation should be kept constant, X and orientation. So we assume the same thing as before, that we are at 0 velocity. And then again, question regarding uniqueness and what the solution is, whether it's the same as the previous one or not. Now, what do we have to do for this? First, we have to take this equation here, which is in joint space, and transform this into task space. And that's something that is straightforward, and it's always the same. All we need to have is the end effector Jacobian. Then you can calculate the end effector inertia. You can calculate your mu, and you can calculate your p. You also need your JE dot. And that's, I mean, we have to have, if I have JP, I can do ddt, time derivative, and evaluate it at Q and Q dot at time t. And then I get my J dot E. And with this, I can get my mu and my P. Once I have this, I have my description in task space. So all I need is to define the acceleration in task space. And this is already given same as before. And then we get with this, we get the end effector force, and we do the Jacobi transposed mapping, and we get the joint level torque. So that means the differences that we have here is simply going either first from task space acceleration to joint space acceleration and then to torque, or you go from task space acceleration directly through the task space dynamics to task space forces and then to task space torques. The advantage of the second way is that you can much better balance end effector forces with end effector motions in the same space. While if you fix the joint level motion, this is not that straightforward, but we'll see this later. Third thing was that we moved on with interaction force control, which means we are combining now this task level description with additional forces that are applied there. And these forces were like we are given a motion here, an acceleration here, and we have two forces. One is a drag force and the other one is producing a normal contact force. And the question was then, what is the joint torque? To go back, there was again one question. Let me solve this first. So how do we get to this one? Well, we have W dot is equal to my X double dot, my Y double dot, and my Phi double dot. This is how I define my task space. I have two positions and one rotation for accelerations. This one must be 0. That's what we said if you don't have a feedback law. This one is defined through this 1 meter per second. And this one is the same, must be 0. That's how we get this W dot. All right, let's go back to this one again, and I directly present you the solution. So what we're doing here is first, again, we define this W dot. Now, in this case, we're not moving in Y double dot, but we're moving in X double dot by minus 1 meter per second. And then I take my task space or my operational space controller, which says, let's define this FE, the operational space force, which is composed of one part here, which is the part that is required to move the system, and there's a second part that is required to produce the force. And again, if we look at our equations of motion, so we have this Fe is equal to our lambda times X double dot plus mu plus P plus, and now all the forces where I'm producing interaction with the environment, Fc, so the contact forces. And these contact forces are now again the ones exerted by the robot onto the environment. So if I have a motion which is in this direction, I get a force which is in this direction acting on my shovel. So this is the force of the drag on the shovel. So what the robot has to produce is the counter force to balance that thing. It has to produce this force here. So minus 1000 Newton. This is where how you can, again, figure out what is the right sign for it. You can also write the whole thing differently if you like. You can write here plus F, so the same plus Fe, you put it on the left-hand side, or let's move like this, we can minus Fc, and now it's force, oops. It's the force on the robot. So the force that acts on the robot. This is then the plus 1000. The normal contact force like my ground produces a force which acts on me, right? I have a force acting on me, which means my shovel has to produce I, as a robot, I have to produce a force which presses downwards. That's why I have here a negative sign. And I'm happy that somebody asks about the selection matrix. So where is now the selection matrix in here? And the selection matrix is typically applied when you have either motion or contact forces. Now in here, it's kind of a mixed solution, right? So we have in normal direction, in this direction, we have only a force, but we have no motion. That means I could make a selection matrix which does the select this normal force direction. And then we have here the one which selects the tangential motion for the motion part, which is the one minus the normal force selection matrix. And what we have here means that, like, here we have a force and here we have zero motion. So that's how the selection worked very nicely for the normal part. It's a bit ugly for the drag part, because in the drag part we have both motion and we have force. So that means there you see both at the same time. You have to add this contact force also in the direction where you have motion, but you don't have the separation as we have seen it in the classical operational space control. But it's no problem, so the formula is still correct. All right, then we move on to the last part, which is now, again, same problem, a couple of questions, which is, I want to hear the least square minimal torque in order to accelerate again with a certain acceleration upwards while keeping orientation in horizontal position. And then we have two special cases. First cylinder is blocked, and the second one is the first cylinder has a hose rupture. So what is the solution to the first one? We write here the task, which is, first of all, the dynamics equations of motion. And we do this in joint space. So this is a linear equality where we have A times X minus B1 equal to 0. That must hold, right? The equations of motion have always to be satisfied. Now I have the second objective, which says accelerate the end effector with 1 meter per second upward. So I can write the second task, which essentially does nothing else than it selects the upwards motion, that's this part, while keeping the horizontal position constant, while keeping the rotation constant. So this is again my W dot star. And I write this now as a function of my X here. So I have my A2 times X minus P2 equal to 0. And as you see in this A vector here, because we have a stack of Q double dots and tau, we have now here the end effector Jacobian in the first part of the matrix, which selects then the right Q double dots. And we have a 0 for the torques, because like this linear constraint that I have here is independent of the torque. And now I want to have the least square minimal torque. So that means my last objective must be minimize the torques. So I have to formulate this minimize the torques as an A3 times X minus B. So what I have to do is I have to select all the torques, and I want this to be minimal, so I have to set it to 0. So I have here my A3 times X minus B equal to 0, while B is also 0. Now what I have to solve is make sure we optimize, we try to fulfill this task as well as possible while ensuring that this task and this task are fulfilled. And I have the tool for doing this. Either I do this continuous projection into null space, or I take a much better optimization toolbox that does consecutive least square optimization, and there you go. Now, second question was, assume the first cylinder is blocked. So what does that mean? First cylinder is blocked means I cannot move joint 1. So the acceleration of joint 1 must be 0. That means my Q1 double dot must be 0. So in order to define that task, I have to identify a selection matrix which selects out of this X vector, this Q1 double dot, and this has to be 0. So I have to somehow squeeze this in my A matrices. So I have the same constraint with the equations of motion. I extend now my second task with this selection matrix that selects my Q1 and sets this to 0. Now the question is this possible or not? Sorry. Is this possible or not? Can we still move? And yes, we can, because here we have 2 times 4, 1 times 4, 1 times 4. So we have here, this subpart here is a 4 times 4 matrix, linearly independent. That means we, as long as we're not in a singular configuration, of course, we can completely fulfill the objective of end effector tracking something, so we can still find the solution. However, if I would have here an additional task which says minimize my tau, that is kind of useless because my task here, this task, already completely fills all the optimization space that I'm having. I cannot further optimize. I have 4 tasks. I have 4 directions in the motion I can optimize. So there's nothing left for my torque. So the question here is whether can I instead set Q1.0 instead of Q1 double dot to 0. The Q1 dot is a state. If you're discussing dynamic control, the Q dot is a state. I cannot directly modify my Q dot. I can only modify my Q dot through changing the Q double dot, and then in the next time step, I have modified the state. But I don't have direct access to my Q dot. And then the last one is, we assume the first cylinder has a hose rupture, which means my tau 1 is equal to 0. I can't produce a torque with that thing. So what is the solution to this one? Again, like we have to somehow embed this through a selection matrix into our A matrix. So I do this, then I have a hose rupture. So my second task is I have a hose rupture here. So I want my tau 1 to be equal to 0. I have a selection matrix for that. And then I have my motion objective, and that's the solution. So this is A1, this is A2, and this is A3. Now you may ask, why do we have now 3 tasks and before we had 2 tasks? So here I was in this one, I was just lazy enough. So what I would do if we would split this further, I would say this is my A2 and this part is my A3, because ensuring that the first joint does not move is much more important than ensuring that my end effector tracks a position. Otherwise, the solution is not valid. In other words, this solution, if I would have here A2 and A3, in a hierarchical manner, that would also generate a correct solution, which is correct with the dynamics and correct with the constraint that the first cylinder is blocked, even if you're in a singular configuration, which means that the third task here cannot be entirely fulfilled anymore. So you would then just try to move the end effector as much as possible as we want, while ensuring that the first cylinder is not moving and the equations of motion are hold. In this third element, we have 3 consecutive tasks, and we clearly give this higher priority than the A3, which means I have to make sure that I try to move, of course, as well as possible, but only without producing torque in my first joint. The question is now, can we still move as we want? And for a non-singular configuration, we can still move like this, like my desired acceleration. And the reason we can do this is that we are accelerating one link with respect to the another link. So this first task here, what this tells us is that my first link of the arm is just falling down because I don't have a torque here at the first joint. However, I can still move my end effector by accelerating the other links with respect to my first link to move along a predefined acceleration. Of course, I cannot do this infinitely long. At some point, I'm just out of motion capacity with the whole system, but locally, I can do this. Why A1 and A2 not the same priority? We can put them at exactly the same priority. This is no problem. So the motion constraints and the dynamics equations of motion can be at the same priority. And in fact, if you're very sure that independent of what you're doing, the constraints and like certain tasks can be assembled into one task with the same priority and it will not change your solution, then I would do it just because of numerical efficiency of the whole setup. But overall, it doesn't really matter too much if you have a clever optimization pipeline in the backend. This will do this for you. With this, I'm closing. So is it actually? So the question is whether it's an underactuated system. So the system has 4 degrees of freedom, but only 3 actuators. So yes, it's underactuated, but for the task we want to achieve, we have 3 actuators and 3 objectives. Although the dimensionality of the joint space is 4-dimensional, we can still with these 3 control with these 3 actuator inputs, we have full authority of locally controlling the 3 end effector accelerations for a certain time period. If you want to fully control the system over a longer time period, you would have to have an MPC controller which takes into account time evolution of that. Another question is whether there shouldn't be another task with high priority to stay in the range of a linear motion on the real system. And yes, that's true. That's actually something that we are doing. So for example, you have, if you go to the task 2 or the question B and C, these are special cases, right? If you go for the first case where we have 3 objectives of moving the end effector position and rotation, and then we have 1 degree of freedom left. What we're doing here is we're optimizing the joint torque. But instead of optimizing the joint torque, I can also have another task which drives my Q towards a Q desired, so a nominal configuration. So I decide my Q double dot to be such that I have a potential field around the desired Q, and then it will try to stay as close as possible to a nominal configuration while fulfilling the end effector task. And that's exactly what happens in avoiding like collisions of individual actuators, joint range limitations. You can also have here nonlinear, like inequality tasks, like Q1 must be greater or less than a Q1 limit. But again, this is on Q level, so I have to somehow bring this on Q1 dot and on Q1 double dot level through barrier functions that are typically applied on that. But this is beyond of what we're discussing in this class. If you're interested in that, come into a research project with us, and you're going to see this in a complex system. With this, I'm closing here. We're going to apply this next week to floating-based systems, and then the over next week to legged system. And I think by then you know this much more in detail. But I think what you have seen here on the very last slide, this is essentially, in my eyes, one of the core outcomes of the controls part that you should learn in this class. With this, thanks a lot, and have a good lunch. Bye-bye.